Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. In this video, we are going to continue with chapter 4, pure bending. Okay, the topic for lecture 3 would be we will be discussing on the members made of composite materials or several materials. So the formula or the derivation that we have learned in the previous part would be based on the assumption of homogeneous materials. Okay, it's all the same one part with one same material, and that cross section or the beam will be having a one given modulus of elasticity E. But if the member is made of two or more materials, of course it will have a different modulus of elasticity E. Okay, we are going to call the member is as a composite member. So now let's consider a bar consisting of two portions of different materials that were bonded together as shown in this figure. So we have material 1 and material 2. It could be one part could be just metal, and another part could be another alloy. And this composite bar are going to deform as described in the previous section. Okay, it will deform as what we have learned. And since the cross section remains the same, we have a rectangular cross section throughout the entire length. And since there were no assumption made in the previous topic regarding the stress-strain relationship of the material or the materials involved. So therefore, we are going to get the normal strain epsilon x are going to vary linearly with the distance y from the neutral axis of the cross section. So we are going to have a linear value of the normal strain, okay, considering the distance y from the neutral axis, and therefore we are going to have the formula here that epsilon x would be equal to negative y over rho, okay, where y would be the distance from the neutral axis. Okay, but we cannot assume that the neutral axis we cannot assume that the neutral axis of this cross section are going to pass through the centroid of this composite. And basically this is one of the main objective in this topic, where we want to determine the location of the neutral axis of a composite member. Okay, so since the modulus of elasticity of the first material given by E1 and the second material as E2, both values will be different, E1 and E2. Therefore, the equation for the normal stress for each materials will be given by sigma 1 for material 1, the stress at sigma 1, the stress at material 1 or the upper part would be equal to E1 times epsilon x. Okay, and if we replace with the previous equation, we are going to get that sigma 1 equal to negative E1 times y over rho. Similarly, for the stress in the second material would be sigma 2 equal to E2 times epsilon x, where this is also equal to negative E2 y over rho. Okay, so the stress distribution curve is obtained, and we are going to find that it consists of two different segments with straight line as shown in this figure. So we are going to have one is the sigma 1, okay, from a distance from the neutral axis, okay, at a distance y would be the maximum for sigma 1, and for sigma 2, okay, it will be overlapping with the materials 1, okay, where we are going to have sigma 2 will also have tensile and also will have a compressive stress, okay, unlike sigma 1, which only have a a tensile. So it follows that okay um, it follows that the force dF1 that is being exerted on an element area of dA of the upper portion of the cross section would be given by dF1 equal to sigma 1 times dA. So this is the elemental force in the first element, in the first material. And we can replace the value of sigma 1 with the one that we have here, and we are going to get negative E1 y times dA over rho. And similarly, we are going to have the same elemental force for materials 2, where dF2 equal to sigma 2 times dA, the area, and this is also equal to negative E2y over rho dA. So we are going to denote that the ratio between the modulus of the material 1 and 2 is given by E2 over E1, and we are going to represent this by N. So we can also write that dF2 is equal to negative N E1 y over rho dA, and this is also equal to negative E1 y over rho and dA. So basically what we want to do is that we are going to find out that the same force dF2 would be exerted on an element of area and dA. So if we compare with the elemental force at material 1, okay, this equation, this equation and this equation, what we are going to find out that for materials 2, okay, the same force is being exerted, except that the area, okay, is multiplied, okay, by the value of N, which is the ratio of the Young's modulus of material 1 and 2. So provided that the width of each element of the lower portion were multiplied by the factor n, okay, we are going to get the same ratio of the force and stress. And we should note that the widening, okay, if n is larger than 1, okay, the materials downward can be transformed okay, it will be wider if the value of E2 is larger than E1, and the transformed cross section are going to be smaller if the n value, the ratio is less than 1. And the widening itself must be in a direction parallel to the neutral axis of the section. So we want to make sure that we stick with the consensus in the previous part, where the deformation of any cross section of beam, okay, would be in parallel with the neutral axis. Okay, why? Because it is essential that the distance y of each element from the neutral axis remain the same. So we want to make sure that the y distance, okay, for both element material 1 and 2 will remain the same. And this new cross section is called as the transform section of the member. So we have the original member section, okay, and we have the transform, where basically what we do is we transform the second materials into the first materials, okay, but we multiply the width of the materials by the value of n. So since the transform section represents the cross section of a member made of homogeneous materials with a modulus of elasticity E1, so now we can use the method that we have learned in the previous part. Okay, and first we need to find the neutral axis of the section. okay, we can use the calculation for the neutral axis, okay, to find the second moment of area. And then we can also find the normal stress at various points, okay, at various distance y from the neutral axis of this transform section. And therefore we can find the stress sigma x at any point in the transform section should be corresponding with the homogeneous materials equation that we learned previously, where sigma x will be equal to negative my over I. So m is the moment, y the distance from neutral axis, and I will be the moment of area. Okay. And in order to obtain the stress sigma 1, okay, sigma 1 is 1 here of the material 1 at a point located in the upper portion of the cross section of the original composite bar. So let's say you want to find the original composite bar, you want to find sigma 1, we can compute the stress sigma x at the corresponding point of the transform section. Okay, easily sigma 1 is equal to sigma x. But for sigma 2, okay, to obtain the value of sigma 2 of the original cross section of the original member, okay, what we need to do is we must multiply by the value of n to the stress of sigma x. Okay, we need to multiply by n. So indeed, okay, if you look at the elementary force df2, okay, and df1, okay, basically it will remain the same, where df2 is applied to an element of area nda of the transform section, and to an element of dA of the original section. So we are going to find out that the stress sigma 2 at any point of the original section must be n times larger than the stress at the corresponding point of the transform section. So original untuk bahagian the one that we have transformed will be n times larger than the one in the transform section. Okay, so now let's take a look at one example. Okay, we have a bar made of bonded pieces of steel. The modulus for steel is 200 gigapascal, and we also have a brass. The modulus is 100 gigapascal. So the steel is in the middle, and the brass is sandwich in between of the steel at both sides of the steel. And we need to determine the maximum stress in the steel and brass when a moment of 4.5 kilonewton meter is applied. So the solution, okay, in order to solve this problem, okay, to find the maximum stress in the steel and also in the brass, first, okay, this is a composite material, so we need to transform this bar into one equivalent cross section made of entirely of brass. Okay, why we choose brass? Because brass is smaller than the modulus of the brass is smaller than the steel. Okay. And then we need to evaluate the cross-sectional properties of the transform section. Then we are going to calculate the maximum stress in the transform section. Okay, and this would be the correct maximum stress for the brass piece. Okay, and then to find the maximum stress in the steel portion, we need to multiply with the ratio of the Young's modulus and EB over ES. Okay. So first we need to transform the bar of an equivalent bar cross section made of entirely of brass. So what we are going to have is we are going to get the value of the ratio n equal to ES over EB, 200 over 100, we should get the n is 2. Okay, now we want to convert this steel into brass. So we are going to make sure that only the width is multiplied. So the original width is 18, so we are going to multiply by 2. Okay, we are going to multiply by 2 and we should get 36 millimeter. The width of the brush will remain the same, 10 millimeter for both sides. So now we have a total width of uh, 10 plus 2 times 18 plus 10, which is 56 millimeter. So the width of the transform section is now 56 millimeter. So note that this change in dimension must occur in a direction parallel to the neutral axis. So we know that the neutral axis is at the center of the height, 75/2. And the moment of inertia of the transform section about its centroidal axis would be equal to I equal to 1/12 VTH cube. Okay, so this is the moment of inertia or area for rectangle. So B will be the breadth of the transform section, which is 56 millimeter, and the height will be the one is not doesn't change from the original to the transform, remains 75, and we are going to get I equal to 1.96 exponential 6 millimeter power of 4. And the maximum distance from the neutral axis C, okay, would be 37.5, half from the total height. And then what we need to do next is to use the equation that we have learned in a previous topic, okay, to find the stress at any point in the cross section. Sigma m, okay, equal to mc over I. So we want to find the maximum stress, sigma m. So the distance should be the maximum distance, which is C, 37.5. So replace the value, we should get the moment is 4,500 Newton meter. The distance is 0.0375 meter. I, the one that we had calculated, and we are going to get the maximum stress is equal to 85.7 megapascal. So this is the maximum stress for the brass, okay, for the brass, because we have transformed all the materials into one homogeneous material, brass. So the maximum stress for the brass would be equal to the maximum stress of the transform section, which is 85.7 megapascal. But how about the steel? So the maximum stress for the steel will be multiplied, okay, will be the maximum stress of the transform section multiplied with the value of N. So the value of N is 2 times 85.7 megapascal, and we are going to get the maximum stress for the steel is 171.4 megapascal, while the maximum stress for the brass is 85.7 megapascal. Okay, the same with the maximum stress of the transform section. Okay, so now it is also important to take a look at our surrounding, where one of the example of composite is the one that have been used to make the buildings, which is reinforced concrete beams. So reinforced concrete beams is one important example, okay, where it used two different materials. Okay, it has steel rods and also it has the concrete. So these beams, when subjected to positive bending moments, will be reinforced by the steel rod, okay, placed at a short distance above their lower face. Okay, we just put down here. Okay, and there is a reason why we put down here, and it depends on the application of the beam. So usually the application of the beam, we are going to have a positive bending moment, okay, a positive bending moment, where the upper part are going to resist a compressive load, okay, while the lower part are going to resist the tensile. So since concrete is very weak in tension, okay, it's going to crack below the neutral surface, and the steel rod are going to carry the entire tensile load. Okay, so the steel rod will cover the tensile, and the concrete part are going to carries the compressive load. So if we want to obtain the transform section of the reinforced concrete beam, what we need to do is we are going to replace the total cross-sectional area AS of the steel bar. So we have the steel bar here, 3 steel bar. We are going to replace this with an equivalent area of N times AS. So we have N times AS. And where N is the ratio of steel modulus over the concrete modulus, ES over EC. And since the concrete in the beam will only act effectively on since the concrete in the beam will only effectively carries compression, so only the part located above the neutral axis would be used in the transform section. So the lower part in the lower than the neutral axis, the concrete, okay, will not be considered. We can assume that it is not functioning or is useless, but we have the rod steel. Okay, we have the rod steel. And then we are going to find out that the location or the position of the neutral axis is a bit tricky to be defined. So the position of the neutral axis then can be obtained by determining the distance x from the upper face of the beam, okay, from here, from the beam to the centroid, of the transform section. And then we are going to use the width of the beam B and the distance D from the upper face to the center line of the steel rod, okay, from the center line to the steel rod, D, applying to the steel rod D, minus with X, and then the first moment of the transform section with respect to the neutral axis must be equal to 0. So basically we are going to get this equation, okay, where the first part is the concrete B times X, the area of the concrete part, the upper part, times, okay, the centroid of the first part of the concrete part, X over 2, minus NAS, okay, the area of the second part at the lower part at lower part of the cross section, times D minus X. Okay, D minus X would be the distance from the neutral axis to the center line of the steel rod. Okay, center line of the steel rod. So we are going to consider steel rod will be usually circle. So we are going to consider the radius of the steel rod. So this should be equal to 0, and it can also be written as half bx square plus NASX minus NASD equal to 0. So by solving this equation, okay, this is a quadratic equation. We have x square. Then we should get two value. One is the position of the neutral axis in the beam. Okay, we are going to find the location of the neutral axis, and then we are going to find the portion of the cross section of the concrete beam that is effectively used in the moment problem. Okay, so the stress in the transform section. So once we know the location of the neutral axis, we can proceed to calculate the normal stress in the transform section. Okay, this is the transform section. And the distribution of the compressive stress in the concrete and the resultant Fs of the tensile forces in the steel rod, okay, is shown in this diagram, okay, in this figure here. We are going to find out that the concrete part, okay, at upper part from the neutral axis will carries the compressive stress, okay, at a distribution, linear distribution, and then there will be no stress being carried in this region, and then we have the steel rods, okay, where the steel rods are going to carries all the tensile load below the neutral axis. So the normal stress will be the same equation, sigma x equal to negative my over I, and the stress for the concrete will be equal to sigma x, but the stress for the original steel rod, original cross section beam, sigma s, okay, will be equal to n times sigma x. Okay, so let's take a look at one sample problem. So we have a concrete floor slab reinforced with 16 millimeter diameter steel rods, and the steel rods is placed at a distance of 40 millimeter above the lower face of the slab, so 40 millimeter from the bottom. The modulus of elasticity is 200 gigapascal for the steel and 25 gigapascal for the concrete. So we can see here that the modulus of elasticity for the steel is relatively higher, okay, than the concrete. Okay, and this value of E should affect in the maximum stress that can be handled by the steel and the maximum stress that can be handled by the concrete. Okay, next, let's proceed with an applied bending moment of 4.5 kilonewton meter for 0.3 meter width of the slab. So we are going to consider only 0.3 meter width. Where this 0.3 meter width, there will be a bending moment of 4.5 kilometer. Determine the maximum stress in the concrete and steel. So we need to find sigma S and sigma C. Okay, maximum. So the solution, okay, similarly, we need to transform this composite reinforced concrete beam into one homogeneous material, which is concrete. And then we are going to evaluate the geometric properties of the transform section. Basically, we want to find the neutral axis and we want to find the moment of area, moment of inertia I. Then we can calculate the maximum stress using the equation, the flexural equation, sigma equal to my over rho, as my over I. Okay, so let's consider the portion is 0.3 meter. Okay, consider 300 millimeter the breadth, and we have the distance is from the upper slab face to the center line of the steel rod will be 100. So how did we get 100? Okay, we need to look carefully at the dimension given here. We have 140. Okay, the length, sorry, the height of the concrete itself, and then we have 40 millimeter of the steel rods. Okay, located here. Okay, so we know that from the upper face slab to the uh, bottom of the steel rods, okay, the distance will be 100. Okay, 100 millimeter. And what we have to do next is we need to find the ratio n, es over ec. So 200 over 25, we get N is 8. And then we want to calculate the area, the transform area of the steel rod. So the steel rod transform area now will be N times AS. So N will be the ratio and AS will be the area of circle of the steel rod. So we have two two steel rods in this width 300 millimeter. So let's take a look back. We have a 300 millimeter. So at the distance or at the width of 300 millimeter, the maximum steel rods that we are going to obtain is only two. Okay, only two. There will be no way to insert three steel rods in this 300 millimeter width. So there will be only two steel rods, and therefore we times 2 times the area of the steel rod by 4 times 16 millimeter square, and we should get the transform cross-sectional area of the rod steel would be 3216 millimeters square. Next, we want to evaluate the geometric properties of the transform section. Okay, we want to find the neutral axis. Okay, where is the neutral axis located in the transform cross section? So we can use the equation that we have in the previous part, in the previous slide. So 300 the width times x, okay, the height of the concrete part, okay, at the upper part of the neutral axis x, times half of the distance to the centroid of the concrete to the neutral axis, x over 2, okay, times the area, okay, times the area, which is 36, minus, okay, the transform cross section of the rod steel 3216 times 100 minus x, 100 minus x equal to 0. And by solving this equation, we are going to get the value of x is 36.8 millimeter. Now we can calculate the moment of inertia I, okay, where we have this equation. Okay, so this is equation that have been simplified. So we have two part here. Okay, basically what we need to do is we need to use the total moment of inertia for a cross section beam. So the simplified version would be 1 over 3 times 300 millimeter the breadth times the area of the concrete, times the distance x of the steel 36.8 millimeter, okay, plus 3216, okay, the area of the rod steel times 63.2 millimeter. So this is 100 minus x. So the first part is the concrete and the second part is the rod steel. So we combine both moment of inertia to get the total moment of inertia of the whole transform cross section. And we are going to get I equal to 12.8 millimeter power 4. Then we can use the value to calculate the maximum stresses in the concrete and in the steel. So in the concrete, it will be MC1 over I. So what is the value of C1? So C1 will be the maximum distance from the neutral axis to the upper face of the slab concrete. So C1 would be equal to X, which is 36.8 millimeter. And then we are going to get sigma C, maximum stress in the concrete is 12.9 megapascal. So 12.9 megapascal is the stress that occur at the upper part of the concrete slab. And then the maximum stress for the steel, okay, will be given by N times MC2 over I. So C2 will be this distance, okay, 100 minus X, 0.0632 meter over I. So we are going to get sigma S is equal to 177.8 megapascal. So this is the stress that is occurring in the rod steel. And then because now we assume that the steel rod is rectangular. Okay. And looking at this result and looking at the distribution, if we want to simulate the distribution, we are going to find out that the upper part of the concrete are going to carry the compressive, while the steel rod are going to carry the tensile load. So we are going to find that the difference between sigma S and sigma C is quite big, it's quite large, and this is mainly caused by the value of the Young's modulus in the previous part, 200 gigapascal and 25 gigapascal. Okay, next we have a stress concentration. So similarly in the previous topic also we have discussing about the stress concentration, where now in this in the pure bending topic, the formula sigma m, this is the formula that we have been using throughout this topic. Sigma m, the maximum stress, is equal to mc over I. For a member with a plane of symmetry and a uniform cross section, is accurate, okay, throughout the entire length of the member. So this is only possible for member that is smooth and have a constant cross section, okay, throughout the length of the beam, okay, of the member. But under other condition of application of the load, stress concentration will exist near the point where the loads are applied. So we also know that higher stresses will also occur if the cross section of the member undergoes a sudden change. Okay, what does it mean by a sudden change? Is that we have maybe a cross member with two particular case. One is a flat bar with a sudden change in the width. Okay, one is in the width. So this is one smooth. This is other. Okay, so we have. So the width is different. And another case is that we have a flat bar with a groove. Okay, either single or double groove. So this is two particular case where sudden change happen through the width of the member. So since the distribution of stress in the critical cross section depends only upon the geometry of the member, stress concentration factors can be determined for various ratio, and the value of the stress concentration constant had been experimented and obtained. And what we have here is that the value of the maximum stress in the critical cross section can be expressed as sigma m equal to k times mc over I. So we have the stress concentration factor k, okay, stress concentration factor k, where the value of k can be obtained from these two graphs. Okay, the first graph is for the first particular case that I mentioned, sudden change in width, or we also call as fillet, and another one is the second case where we have groove or notch. So we can take a look at the at this graph here. So for fillet, we are going to consider the ratio of the radius of the fillet r, okay, over the diameter or the width of the smaller portion. Okay, and we also going to consider the ratio between the larger width over the smaller width. So if we look at this graph, okay, there will be several curves that we have to select from, and from this graph we can obtain the value of k, which we can later on use in our equation to find the maximum stress due to the concentration in the fillet, okay, at the fillet. Similarly for groove, okay, we are going to consider the ratio of r over d, the radius of the groove over the distance of the groove part d, small d, and also the ratio of the larger portion of capital D over d. So both graph shows that it is very important to use fillets and groove that have a radius r, okay, this radius r here, as large as possible, as practical, okay, in the application. So the larger the value of r, okay, the larger the value of r, we are going to get the value of k will be smaller. So once the value of k is smaller, the maximum stress due to the stress concentration will also be smaller, and therefore it will help in designing or using cheap material for any kind of application. Okay, so we have finished with this lecture. So I have two question quiz for you to answer. So the first question would be a beam, W beam. So we have allowable stress 155 megapascal. Neglect the effect of the fillet stress concentration. Determine the moment of inertia I, and then determine the largest bending moment M that can be applied to the wide flange beam shown. So basically you have to understand the video or the contents in the lecture 1 and lecture 2 video to answer this question. Okay, next, the second question is regarding the stress concentration. So we have a bar with a groove of 10 millimeter deep cut in a steel bar which is 60 millimeter wide and 9 millimeter thick as shown in the figure. So this is the cross section. Determine the smallest allowable width of the groove if the stress in the bar is not to exceed 150 megapascal, when the bending moment M is equal to 180 Nm. So these two questions must be answered, and please submit your answer in PDF file using the submission pod that I prepared in the canal. So that's it for the lecture 3. We are going to continue with our final lecture on this pure bending topic before we proceed with the next chapter, beam. So that's it for this video. Thank you and see you again.